Hello students, today I am going to give a lecture on modules of finite length. I will start my lecture with the definition of simple module. A module M is called simple if it is non-zero and it has no submodules other than 0 and M. Here are some trivial examples of simple module. First example is any one-dimensional vector space is simple. Any minimal submodule of a module is simple. And if n is maximal submodule of M, then M mod n is also simple. Now next is a trivial observation for a non-zero simple module. A non-zero module M is simple, 0 is maximal submodule of M is minimal submodule of M, and every non-zero element of M generates M. These four conditions are equivalent. That is, we can say that if M is a non-zero simple module, then 0 submodule will be maximal submodule of M. The M will be minimal submodule of M. And if X is a non-zero element of M, then the submodule generated by X will be M. So I am leaving the proof for you people. These conditions are very easy to prove to be equivalent. Now, simple modules exist in a non-zero Artinian module, whereas simple quotients exist for a non-zero Noetherian one. What does this mean? Now, we know that if M is a non-zero Artinian module, then minimal submodules exist in that M. And since we have seen that minimal submodules are simple, so therefore we can say that in a non-zero Artinian module, we can talk of simple submodules. Whereas, if M is a Noetherian module, then it contains maximal submodules. So if N is maximal submodule of non-zero Noetherian module M, then M mod N will be simple. So thus, for Artinian modules, we can talk of simple submodules, whereas for Noetherian ones, we can talk of simple quotients. Next, I am going to define composition series. Suppose M is any module. Then, by a composition series of a non-zero module M, we mean a finite descending chain of submodules of M, starting with M and ending with 0, like M is equal to M naught, contains M1, contains M2, contains MM is equal to 0, such that Mi mod Mi plus 1 are simple for all I. That is, M mod M1 is simple, M1 mod M2 is simple, and so on. This M is called length of this series. So, if M is a non-zero module, then a descending chain of submodules of M starting with M and ending with 0 is called composition series if the successive quotients are simple. Now, observe that suppose M is a non-zero module, then a composition series may or may not exist for M. But if composition series exists, then it will be descending chain of submodules like this. Now here we can see that M mod M1 is simple. Therefore, M1 is maximal submodule of M. Similarly, we can see that MM minus 1 mod 0 is simple. That is, MM minus 1 is simple. So, if M has a composition series, then it would have a simple submodule and a maximal submodule. Now, suppose V is a vector space having a finite basis V1, V2, Vm. Then we consider Vi to be subspace of V spanned by Vi plus 1, Vi plus 2 up to Vm. Then observe that V naught will be what? Span of V1, V2, Vm, which is same as V. V1 will be span of V2, V3 and so on. And Vm minus 1 will be span of Vm, and Vm will be 0. So, we will have a series V contains V1, contains V2, contains Vm is equal to 0. Now observe V quotient V1. Now dimension of V will be M and dimension of V1 will be M minus 1. So dimension of V mod V1 will be 1. So V mod V1 will be vector space of dimension 1. And we have seen that any vector space of dimension 1 is simple. So V mod V1 will be simple. Similarly, V1 mod V2 will be vector space of dimension 1. So it will be simple. So thus, this is a composition series of vector space V. Now, let us consider an infinite cyclic group. This example says that an infinite cyclic group cannot have a composition series. Suppose G is infinite cyclic group generated by A. Then this G will have no minimal subgroups, because suppose G has a subgroup, then it will be cyclic and let it be generated by AI. If I say that this subgroup is minimal, then this is not true, because if AI is subgroup of infinite cyclic group, then AIK will also be subgroup of this. So thus, any infinite cyclic group cannot have any minimal subgroup. So thus, it cannot have a composition series, because we have seen that if a module has a composition series, then it should have a simple submodule and a maximal submodule. So thus, an infinite cyclic group cannot have a composition series. Now, third example, every finite abelian group has a composition series. So let M be a finite abelian group of order n. We will prove this result by applying induction on n, order of n. Suppose n is equal to 2. So M will be a group of order 2. So M will have a composition series M containing 0, because any group of order 2 will be cyclic group of prime order and will have no subgroups. So thus it has a composition series M containing 0. Now suppose the result is true for every abelian group whose order is less than equal to n minus 1. That is, if G is any abelian group whose order is less than equal to n minus 1, then it has a composition series. Now let us consider the case when the order of group is n. Now we consider two cases. If M is simple group, then M containing 0 will be composition series for M. If M is not simple, that means it will have a proper submodule other than 0 and M. So by applying John's lemma, we can say that M has a maximal submodule. Let that submodule be n. So now we consider M mod n. Since n is maximal submodule of M, M mod n will be simple. And since n is maximal submodule of M, order of n will be strictly less than order of M. So by induction, n will have a composition series. And let that composition series be given by this. Since n is maximal submodule of M, so if we add one more term, namely M, to this series, then this will be composition series of M, because M mod n is simple and the successive quotients of this series are simple because of this. So thus we have obtained a composition series for M. So thus we have shown that any finite abelian group has a composition series. Now, let us define modules of finite length. We will say that a module M is of finite length if it is either a zero module or it has a composition series. So thus, by the examples we have discussed earlier, we can say that if we have infinite cyclic group, then it is not this is not a module of finite length. So a module is said to be of finite length if it is either 0 or has some composition series. Now, we will show in this theorem that a module is of finite length if and only if it is both Artinian and Noetherian. So if a module is both Artinian as well as Noetherian, then it will be of finite length. Let us prove this. Suppose M is of finite length. If M is 0, then the result is obvious because a 0 module is both Artinian and Noetherian. So suppose M is non-zero. Since M is given to be of finite length, this means M will have a composition series. Let this be the composition series of M. Now, we will prove our result by applying induction on length of this composition series, which is M. If M is 1, if the length of this composition series is 1, then M will be simple, because then we have only two terms in this. M equal to M naught containing 0. So M will be simple, and we know that a simple module is both Artinian and Noetherian. So the result is true for M is equal to 1. So we assume that M to be greater than equal to 2 and assume that any module which has a composition series of length less than equal to M minus 1 is both Artinian and Noetherian. Now we prove the result for this M. Now look at M1. M1. M1 has a composition series, namely this, of length M minus 1. So by induction, M1 is both Artinian and Noetherian. Also, M mod M1 is simple. So it is also both Artinian and Noetherian. Now we know that if M is a module with submodule N such that N and M mod N are Artinian or Noetherian, then M is Artinian or Noetherian. So thus here we get that M mod M1 is Artinian as well as Noetherian, and M1 is also Artinian and Noetherian. So M will be both Artinian and Noetherian as required. So thus we have shown that if a module M is of finite length, then it is both Artinian and Noetherian. Let us prove the converse part. Suppose module M is both Artinian and Noetherian, and we want to show that M is of finite length. That is, we want to show that if M is non-zero, then it has a composition series. So let M be non-zero. Now since M is Noetherian, so it will have maximal submodule. Let that submodule be M1. Now there are two possibilities. Either M1 is 0 or M1 is non-zero. If M1 is 0, then M will be simple and hence it will be a module of finite length. If M1 is non-zero, then being a submodule of Noetherian module, it will be Noetherian. So it will have maximal submodule, say M2. Again, if M2 is 0, then M will have composition series, namely M containing M1 containing 0. If M2 is non-zero, again, using the same argument, we will get that M2 will have a maximal submodule. So at any finite stage, if Mn is not 0 for any n, then we will get a maximal submodule Mn plus 1 of Mn and so on. So thus we will get infinite descending chain of submodules, namely M0 containing M1 containing Mn and so on. But we are given that M is Artinian. So M is Artinian means descending chain condition holds for M. That is, any descending chain of submodules of M is stationary. So thus, if we will get infinite descending chain of submodules of M, then it will contradict the fact that M is Artinian. So thus, Mn has to be 0 for some n. So this means M will have a composition series. So thus we have shown that M will be of finite length if and only if it is both Artinian and Noetherian. Now let us next prove that any submodule and quotient module of finite length are also of finite length. So first of all, we will prove that submodule of a module of finite length is also of finite length. So let M be R module of finite length, and suppose it has a composition series M equal to M0 containing M1 containing MM equal to 0. So here we have M mod M1 is simple, M1 mod M2 is simple, and so on. Let N be submodule of M. We want to show that N is also of finite length. So we intersect series 1 by N. So we will get a series n equal to n intersection m naught containing n intersection m1 and so on. Now, for each I we have the following. Either n intersection mi is equal to n intersection mi plus 1, or if these are not equal, then we consider a map from n intersection mi to mi mod mi plus 1 defined by gamma x is equal to x plus mi plus 1. So gamma will be our linear map and kernel of gamma will be n intersection mi plus 1. So we will get that n intersection mi mod n intersection mi plus 1 is isomorphic to gamma of image of gamma. But image of gamma is a submodule of mi mod mi plus 1, which is given to be simple. So therefore, image of gamma will be 0 or mi mod mi plus 1. But since these n intersection mi is not equal to n intersection mi plus 1, so gamma, image of gamma cannot be 0. So image of gamma will be isomorphic to mi mod mi plus 1. So thus we have, if n intersection mi is not equal to n intersection mi plus 1, then this quotient will be isomorphic to mi mod mi plus 1, which is simple by 1 because 1 is given to be composition series. So thus we have obtained that n intersection mi mod n intersection mi plus 1 is simple. So deleting repetitions in series 2, we get a descending chain like this. N equal to n intersection m naught containing n intersection mi1 containing n intersection mir equal to 0, where n intersection m naught is equal to n intersection m1 up to n intersection mi1 minus 1 and so on. So thus we have obtained a composition series of n. That means n is of finite length. So thus we have shown that submodule of a module of finite length is of finite length. Similarly, we will prove that quotient of module of finite length is of finite length. So let n be submodule of m. M is a module of finite length. So we consider the natural homomorphism from m to m mod n. And we consider the image of series 1 under eta. Now, by 1, we get that eta m will contain eta m1 will contain eta mm. That is, m mod n contains eta m1 contains eta mm. Now, let us see what should be the image of m1 under eta. M1 is a submodule of m. We know that there is one-to-one correspondence between submodules of m containing n and submodules of m mod n. Now m1, eta m1 will be submodule of m mod n. So it should be something like this, m1 plus n mod n. Similarly, eta mm should be mm plus n mod n. Now, again, as in the previous step, for each I, either we have this n plus mi mod n is equal to n plus mi plus 1 mod n, or if these are not equal, then by considering this map, we can see that n plus mi mod n plus mi plus 1 mod n is isomorphic to mi mod mi plus 1, which is simple. So deleting repetitions, we will get a composition series of m mod n. So hence m mod n is of finite length. So thus we have shown that quotient module of a module of finite length is again of finite length. Next, we prove that if n is a submodule of module m, which is of finite length, and m mod n is also of finite length, then module m is of finite length. See, this clearly follows from theorem 1, in which we have shown that a module is of finite length if and only if it is both Artinian and Noetherian. Using this, this proof directly follows, because if n is of finite length, then n is both Artinian and Noetherian. If m mod n is of finite length, then it is both Artinian and Noetherian. So combining the facts, we will get that m is both Artinian and Noetherian. So m will be of finite length. But we want to prove this result by giving explicitly the composition series of m using the composition series of n as well as m mod n. So let us see how. Let n be a submodule of m such that n and m mod n are of finite length. Suppose n has a composition series of length n and m mod n has a composition series of length m. So suppose the composition series be n equal to n naught containing n1 containing up to nn equal to 0 and m mod n containing m mod n1 and so on. With the help of these two composition series, I want to get composition series of m so that I should be able to prove that m is of finite length. Now again, let us consider the natural homomorphism eta from m to m mod n. For each I from 0 to m, we define mi to be eta inverse m mod ni. We consider the pre-images of all of these submodules of m mod n. We name it as mi. So, applying eta I inverse here, we will get that m contains m1 contains mm equal to n, because here eta inverse 0 will be n. Now, here now we induce the composition series of n. So we will get that, okay, observe that mi mod mi plus 1 will be isomorphic to m mod ni mod m mod ni plus 1, which is simple, by the composition series of m mod n. So thus, the successive quotients of this series are simple. Now inducing here the composition series of n, we will get composition series of m like this, which will be of length n plus m. So thus in this we have shown that if n has a composition series of n terms and m mod n has a composition series of m terms, then the composition series of m will have m plus n terms. That is, length of m is equal to length of n plus length of m mod n. Next we prove Jordan-Hölder theorem. It says that any two composition series of a non-zero module are equivalent. Equivalent in what sense? That if we have two composition series of a module m, say m equal to m naught containing m1 containing so on, and m equal to n naught containing n1 and so on, then first of all the length of these two series are equal, that is n is equal to m, and thus the quotients are isomorphic in some order. That is, m mod m1 will be isomorphic to ni mod ni plus 1 for some I. Similarly, m1 mod m2 is isomorphic to nj mod nj plus 1 for some j, and so on. So if m is a non-zero module having two composition series, then those two composition series are equivalent. So let us prove this. We will prove the result by applying induction on length of any two composition series of module n, say m. If m is equal to 1, then m will be simple, so n1 will be 0, and hence the result is proved. Now we assume that m is greater than or equal to 2, and the result is true for any non-zero module having composition series whose length is less than or equal to m minus 1. Now look at the two composition series of module m. Now two cases arises. If m1 is equal to n1 and if m1 is not equal to n1. Suppose m1 is equal to n1. Then m1 and n1 will have composition series this. M1 will have two composition series, one this, because M1 is equal to N1. And since length of the first series is equal to M minus 1, so by induction we will have M minus 1 is equal to N minus 1, and the quotients are isomorphic in some order. So thus the given two composition series will be equivalent, because M minus 1 is equal to N minus 1 will mean M is equal to N, and M mod M1 will be same as M mod N1, because M1 is equal to N1. So in this case, those two series are equivalent. Now suppose M1 is not equal to N1. In this case, we consider a submodule M1 plus N1. This is submodule of M containing M1 and N1. But see, since M1 is maximal submodule, because M mod M1 is simple and N1 is also maximal, so therefore M1 plus N1 will be whole of M. Now look at M mod M1. This will be M1 plus N1 mod M1. This will be isomorphic to N1 mod M1 intersection N1. And similarly, M mod N1 is isomorphic to M1 mod M1 intersection N1. Now, we name M1 intersection N1 as K. This is submodule of M1 as well as submodule of N1. And length of K, K being a submodule of M1 will be submodule of M. M is given to be module of finite length, so K will be of finite length. So K will have composition series, say K equal to K naught containing Kr equal to 0. Now, consider this. M equal to M1 plus N1 containing M1 containing K containing K1 containing Kr to be 0. This is given to us. This is given to us. And M equal to M1 plus N1 containing N1 containing K containing K1 containing Kr equal to 0. Now, the first two are equivalent by case 1. The last two are equivalent by case 1. And the first and third are equivalent because the first and third are equivalent. Similarly, second and fourth are equivalent. So thus we get that all of these are equivalent. So in particular, second and third are equivalent. So thus we have shown that any two composition series are equivalent for a module of finite length. Next, I am going to define length of a module. Suppose M is module of finite length. Then length of any of its composition series is called length of module. Now, because of the previous theorem, we can say that if a module of finite length has two composition series, then length is invariant. So we define this to be LRM. Now, these are trivial facts. Length of M is greater than or equal to 0, and it will be 0 if and only if M is 0. Length of M is 1 if and only if M is simple. Now, let N be a submodule of module M of finite length. Then we have already proved that length of M is equal to length of N plus length of M mod N. So thus, length of M mod N is length of M minus length of N. Or we can say that if N is submodule of module M, then length of N is less than or equal to length of M. And equality occurs if and only if M is equal to N. Now, consider M1, M2, Mn to be submodules of module M, where M is of finite length. Then length of the sum of these modules is less than or equal to sum of the lengths. And equality holds if and only if this sum is direct. So this can be seen easily. We will prove the result by applying induction on N. Suppose N is equal to 2. Then length of M1 plus M2 is equal to length of M1 plus length of M1 plus M2 mod M1. which is equal to length of, okay. Now suppose the result is true for n minus 1 modules, and we write length of summation mi to be length of n minus 1 submodules plus mn. So by induction, okay, we write sum of these n minus 1 submodules to be m dash. So length of summation mi, I going from 1 to n, will be length of m dash plus mn, which is equal to length of m dash plus length of mn minus length of m dash intersection mn. So this will be less than equal to length of m dash plus length of mn. By induction, length of m dash is less than equal to sum of lengths of these n minus 1 submodules, which is equal to sum of this. So that's done. And we can see that if the sum is direct, then m dash intersection mn will be 0. So length of this will be 0. So equality will occur here if and only if the sum is direct.